would like to talking about the networking part. And the topic today will be the programmable data plane. Okay. So before that, I will maybe talking about what we did of the past 5 years on what we do the open control plane. Okay. This is the data center networking evolutions. I believe you guys are much more familiar than me on this kind of pictures. This is actually the why box the story began about 5 and 6 years ago. And the QCT, we deliver our hardware boxes, and based on the open network installation environment all needs, we decouple our hardware, and we're working with the third-party software guys. So on this page, we know that we can provision our hardware and decouple with the softwares, and the software third parties, including the open source of the software, including the ONL, Open Network Linux, including the Ubuntu, or even the proprietary third-party OS. And on top of the open OS, we even can find more and more app providers, such as for some legacy protocol of the app, or for some network virtualization, network automation, and the data center orchestrations. So what we deliver the hardware gears, we even based on the merchant silicons, the broken ones, and we put on top of this, we put the CPU from the Intel or previous from the PowerPC ones. And the goal of this page that is we unlock the vertical vendor locking stories. So the end user can easily find our hardware and working with any our third-party OS partners. This page is we call the open control plane. In this page, I'm not talking about OpenFlow, but talking about what the open OS adoption of our hardware gears. So you may see that in this page, there are almost 10 software partners. They are already running their software in our set of hardware gears. So that we make it happen over the past 5 years, we call the open control plane. But today, even more important what we're talking about is about the programmable data plane. Okay. So this is the brief view of our product lines. So we build a switch from the pizza box to the chassis switches. We deliver the switch from the Giga, 10 gig, 40 gig, and even 100 gig switches for our mega data center users. And the control plane size, the CPU size, previously we have based on PowerPC, but we changed to the x86 about 5 years ago, and we even involving our CPU adoptions, even in size. So the switch in this page are all available now, and then I'm talking about why we want to build a single skill switch as a building block for the mega data center guys. You may ask me why we needed a single skill of the switch as building block. Per our experience for some data center guys, they bought a lot of switch from our single skill switches. As a building block, they can put their switch on the different tiers of the spine, the leaf, and for sure the top or rack switches. So why we need it? The benefit of a single skill switch as a building block is to reduce the capex through the economic scale. You can buy a single skill switch for different kind of deployment. And also the benefit to reduce the OPEX from the software development, service provision, and the troubleshootings. So based on this kind of the deployment concept, why we needed a programmable data center, programmable data plane. Because since each skill, the single skill switch as a building block, but you put this kind of building block on different positions of the data centers, you may want to provide different kind of applications. So for different kind of application, you may need a different kind of data plane, and each application requires different database. But we want to make sure that this different kind of application on different data plane and database could be achievable on the unified hardware gears. So this is the first reason that we want to make it programmable. So we also want to tune the operation to tune the operation of fabric to best fitting the application to fulfill the business requirement. So the goal of this one is from the purpose build of switch to the purpose programmable. So the purpose programmable makes the unify the single SKU data set as a building block achievable. Okay. This is an example about how the different application why require different database. So on this page, I put 5 applications here. So the first one is about the data center interconnections. The switch could be as a IPv4 routers and to connect the data center to data centers. You may find that there is a pipe in between that. You may need a lot of forwarding decision tables. Okay. And the second application about the VTAP routers, we call the RIA. It's kind of a VSLA routings. This is located on top of rack to handle the virtual machine vMotions. You may need a lot of number of tunnels, the VSLA tunnel or the NVGIE tunnels. The third application about the carrier called edge, the edge routers. So we need to handle the MPLS segment routing for IPv6. Okay. And the number 4 application about carrier Ethernet switch router. This is for the carrier, for the telecoms. You need to build a lot of layer 2 VPN, layer 2 tunnels. So, and then the final application about the NAT and the PAT. So this is for the IP address translation and the port translations. Inbound to provide the private IP and outbound to provide the public IP. So this is a kind of a gateway application. So you may find that the different applications need different kind of the portion of the database. So the forwarding decision, number of tunnel, and the service classification are all needed, but the percentage will be different. That's why we want to make sure that the database need to be centralized instead of distributed. Because you can centralize and then you can share the common pool, then you can well utilize your applications. So this is the second reason why we need a programmable data plane. Then another reason why is about the emerging network virtualization. We know that there are different kinds of tunnel of the overlay technology happen, right? Maybe 10 years ago, we know that a layer 2 over layer 2, we know the relay staking, and we also know the MAC and or maybe the layer 2 over layer 3, the VSLA and NVGIE, and even layer 3 over layer 3. So you may find that there are different kinds of tunnel happens. And the job of the IEEE, IETF, and ITU is to define the new standard of the tunnels, not make chip vendor busy, and then make our switch vendor, such Quanta, QCT, busy. So it's very busy, right? So this is just an example of the different layers of the virtualization make everybody busy. But if our data plane is programmable, like this, we can future-proofing this kind of layer virtualization happens. Okay. And also, we found that for the SDDC, that we need more telemetry and analytics for the instrumentations. And the network overlay and the metadata is very important. And we want to improve the load balance and the traffic engineering. Also, we want to make sure the database, as I mentioned on this page, to be common pool-wise and reconfigurationable. So that's why the programmable data center, programmable data plane is so important. And the ultimate goal is to adding a new component, new features, or even new service without any traffic loss or architectural change. This is the ultimate goal. Okay. Then this is the goal about. This is a goal. We know the programmable data is very important, but we want to sacrifice the other key factor of the networking qualities. We still want to make that the throughput is still high, the latency is still low, and the consistency. And the capacity need to be higher. Buffer need to be higher, and most importantly, we want to achieve the low power consumption at a low cost. So talking about the programmability, we know that the FPGA is supposed to field programmable by native. But you know the penalty of PGA is kind of power consumption and cost. And we know even the packet processor even can did the best to handle the programmability, since it's a software-based through the microcode to handle the packet. And even the packet processor is better for the deep packet buffers. But the trade-off is the cost and the latency. So there is no single chip can well handle all the features, key elements. But our goal is to make it balanced, to achieve this key element, balanced and achievable. Okay. Then this is the commercial time, our box. By leveraging Broadcom latest chip, the Trident 3, we have development and working out the two boxes based on Broadcom Trident 3 silicons. And this is the first box that we developed. And this is also on the demo areas. This is a 32 portable 100G switches. And the redundant on the fan and the power. Okay. This is very ideally for the programmable switches and for the top of rack and for the spine switches, since it also can be very good as the building blocks. Okay. And the CPU inside is from the Intel rendering. This is the second box that we can provide the programmability. This is native 25 GB base by 48 ports, and the 100 GB by 8 ports of uplinks. Then, I want to tell you how smart the programmability is of our two boxes. So first, the 80 new component, new feature, and the new services, traffic loss, and no architecture change. And the pipeline is programmable, and that can efficiently mapping the switch process operations. And the database is centralized, that you can utilize the different application of the database needed. And it also provides the instrumentation, the telemetries, overlay, and load balance features, reconfigurable. And this is our box, the X7 and X8 programmable architecture for the SDDC. First, this is a future-proof support. Nobody knows that IETF or IEEE will make any new standard over maybe 2 years or 3 years. So we keep this kind of the space to programmable when the standard is well defined, finalized, then we can programmable to make the ASIC achievable. So we know that the software is very important to handle the ASIC as available. But before that, you need to make sure the hardware need to be capable. So today I'm talking about how to make the hardware capable for different kind of application now and in the future. That's why we need a programmable data center. And the second achievement is about the data center reconfiguration with large table size. The table size is very important for layer 2 and layer 3 tables. But that there are different kinds of packet. IPv4, IPv6, layer 2, and the layer 3, and MPS. All of this table need to be centralized and they could be configurable. Okay. And also the enhancement about the load balance and the control plane enhancement. We increase the bandwidth between the switch chip and the CPU. And the MPS segment routing also enhanced. And the last item is to increase the visibility of the packet through the broad view. Okay. This is a programmable engine of our two programmable switches. So on the egress side, there is a parser. The parser is programmable. And on the middle, there are multiple pipelines. Through the flexible decision logic, we can programmable the lookup engine for the make and actions. And the final stage, the egress side, is the packet editors. So the goal of the packet editor is to make sure that different overlay, the different header of the overlay could be editable. Okay. This is a program component of our two boxes. The first one is packet parsing. So if we look at the green block, the green block in the previous version of the switch, this green part, actually they are configurable, but not programmable. But on our new two boxes, the packet parsing is programmable, and also the make and action lookup table is programmable. And in the final stage, the packet editing are programmable. So there are totally 5 stages of a pipeline inside this silicon, and the 3 is before the buffer, and the 2 is after buffer. And the buffer in the middle is a fully shared. Okay. Additional programmability in the future. Okay. There is an example of three examples. The first one is 5088 version 3. This is increase the time stamping through the packet time stamping. This is also a new standard by IETF. Okay. Oh, sorry, by IEEE. The second one is ER version 3 that increase the visibility, the monitor of the packet. The third one is the PPPoE. PPPoE is very important for the remote access. And we even can route the PPPoE packet to the VSLAN packet. So to do the encap and the decap. So I didn't put the schedule on this page. That make my life easier. Okay. But it's a future proven, okay? And this is the key feature of our 2 boxes. Key features. First one, instrumentation is better. Second one, the field upgradable. Okay. Third one, the buffer is increased. Okay, increase the packet buffer to make the packet buffer is deeper that the packet could be lossless. Okay. And the table of the layer 2 and the layer 3 is increased. We also enhance the ampere schema routing. This is very important for some carrier applications. For the ISP, they need the ampere schema routings. And also the VSLAN routings is also improved. This is a very important feature for the top of rack switches. If you want to handle the virtual machine, to make that the virtual machine is seamless migrations from server 1 to server 2 on the different rack, then the VSLAN routing is very important. And we enhance the control plane, the bandwidth, and the dynamic balance. Also, the software error robustness is also improvement. This is our technology milestone. Over the past decade, QCT we built from the blade switches. Then we built the pizza box switches, 1U type. And we also built the 2U box and even the 6RU chassis switches. And the last year, we built our first chassis switch, provide 128 port of the switch as aggregation switches. And this year, our technology milestone is programmability switches. And the next year will be 400 gig and 10-4-based switches. Okay. So, and even more, it will be higher density and beyond. This is my last page of a presentation. Thank you.